All right, good evening and welcome everyone to Mount Washington Observatory's Science in the Mountains lecture series. And welcome tonight to the program. My name is Brian Fitzgerald and I'm the Director of Education here at Mount Washington Observatory. And joining us this evening to discuss the Observatory's regional Mesonet is the Observatory's Director of Technology, Mr. Keith Garrett, and also the Director of Weather Operations, Mr. Jay Broccolo. Thanks so much for joining us for tonight's program. If you're not already familiar with the observatory, Mount Washington Observatory is a private, nonprofit, member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way we accomplish this is through operating our Summit Weather Station with around-the-clock weather observation and forecasts. Also, our Mesonet, which we'll learn about more tonight, by conducting research and product testing, and by developing and offering innovative educational programs. If you have questions for our speakers this evening, if you're joining us through Zoom, please be sure to use the Q&A button that you can find at the middle of your Zoom screen there, just down at the bottom on the toolbar. Please feel free, you can submit questions at any point. You should be able to actually see everyone's questions as they bubble up through tonight's program, and you're welcome to also upvote a question if there's a question you'd really like to see answered through the program. If you're joining through Facebook, thanks so much for joining that way. Unfortunately, we won't be able to get to your questions during the live program, but we'll follow up with some answers as soon as we're able to after the program. If you'd like to connect for another program through Zoom next time, please make sure you register over at mountwashington.org/SITM. Alrighty, well, before we get going with tonight's program and before we hear from our speakers this evening, we did put together a poll for you tonight that if you're joining us on Zoom, you should be seeing some questions pop up in front of you now. Questions, the first question here, as always, we're curious where you're joining from. Perhaps it's a state within New England, perhaps it's outside of the region here, outside of New England, or perhaps you're joining from outside the US of A. A few more questions for you. One, we're always curious, where do you like to get your weather information from? Throw out a few examples for you. It could be anything from your phone's built-in weather app to the National Weather Service. Maybe it's a website or a company like AccuWeather or the Weather Channel. Maybe it's from the observatory ourselves here, or maybe it's not listed here. Perhaps it's through a broadcast meteorologist that you like through your local news or through the newspaper or elsewhere. And then a couple questions pertaining to tonight's program. How many automated Mesonet stations does the observatory operate? Is it 7, 10, 18, or 22? And then finally, what is a major challenge to operating remote automated weather stations in the White Mountains? Is it primarily extreme cold? Is it extreme wind? Is it insects and rodents? Is it getting to the sites themselves? Or is it all the above and maybe even a few things not listed here? We'll give you just a few more seconds. I see quite a few of you have participated. Thanks so much. And we'll give you maybe 3 more seconds to finish up. And we'll end it in 3, 2, 1. All righty, let's see what we ended up with here. I'll share some results for everybody on Zoom. We can see the Granite State is well represented. A little more than a third of participants this evening joining from New Hampshire. Quarter of you joining from outside of the region as well. Good representation all throughout New England, throughout the rest of the country, and even a couple folks from outside the US. So thanks so much for joining. Now, in terms of where do you like to get weather information from? I have to say I'm very curious about the outcomes here. It looks like the winner here, your phone's built-in weather app. And I have to say, I certainly check that all the time, and a variety of other resources here listed as well. Coming in second place was the National Weather Service. Quite a few of you like the AccuWeather, 15% of you, 11% like the observatory as a place to go, Weather Channel not far behind, and still around 10% or so for resources not listed there. So wow, pretty interesting mix of resources, certainly all places that you can get a variety of weather information from. And then on to our trivia for tonight. How many automated Mesonet stations does the observatory operate? Well, most of you thought it was 18 this evening. We'll see when we hear from our speakers in just a little bit. And then last but not least, what's a major challenge to operating remote automated weather stations in the White Mountains? Well, most of you thought it was all the above and more. Well, we will have to wait and see here. So I'll stop sharing. And in fact, with that being said, I'd love to go ahead and welcome our first speaker for tonight. That's Keith Garrett. Hey, Keith. Keith's our Director of Technology and one of the main players behind the Observatory's regional Mesonet. Hey, Keith, how's it going?
Doing well. How are you doing tonight, Brian?
Great. Hey, thanks so much for putting together a presentation and sharing a little bit about your work. Feel free, take it away.
All right. First, I'd like to say that I actually use the National Weather Service website for all of my weather information. I just don't like the phone apps, but that's just me.
Yeah, well, we'll have to ask Jay too when he speaks, but he likes. Something tells me he's going to give another answer too.
All right, just give me a second to get this set up and ready to share. All right, just like to make sure that you guys can see that.
Looks great.
All right, so again, welcome. Thanks for joining, everybody. Again, my name is Keith Garrett. I am the Director of Technology here at Mount Washington Observatory. My background is information technology, servers, networks, databases, and here at the observatory, I get to work with all kinds of fun and interesting equipment, anything from small radars to lasers and everything in between. So it's quite exciting, and I'm really happy doing this. And I've been doing IT again for about 25 years, and working in the extremes of Mount Washington is just an exciting challenge. So most of you are aware Mount Washington experiences extreme weather all the time. As Mark Twain said, if you don't like the weather in New England now, just wait a few minutes. So most of the weather systems across the United States end up in New England, which earned us the catch line of the tailpipe of America due to the pollution in the 70s, all of it exiting through New England. And with the surrounding terrain and Mount Washington being the most prominent peak for about 1,000 miles, and due to the topography, we have extreme winds and conditions. And New Hampshire's economy is heavily dependent upon travel and tourism, and accurate forecasting is necessary for our region, and it requires as much data as possible. For this reason, as well as climate monitoring, the Mount Washington Regional Mesonet was developed in 2003 in coordination with Campbell Scientific. So what is a mesonet? I hate defining things using the same term or root, but it is a network of regional weather stations that are assembled, and the data is collected to report measurements across a mesoscale area. And I'm going to let Jay go into more detail about that. Again, I'm IT, so not weather, but I do love working with the equipment. Right now, we currently operate 18 automatic weather stations. So that answers one of the questions. And what you're seeing here is an example of one of our displays on our website for the Mesonet information. If you go on to mountwashington.org and look for Mount Washington Regional Mesonet, it'll bring you to this page, which has an embedded Google map, where you can choose the different data that you'd like to display and pan around and zoom in on stations and see what they're currently reading. As you can see, the green ones are stations that are currently reporting. The red ones are ones that are either offline or not currently reporting. Overall, we're spread out quite over a vast area, about 400 square miles of the White Mountains, primarily on areas of heavy exposure and higher elevations. The harsh and varying conditions of the White Mountains create these really unique operating conditions for the stations, and they can be extremely difficult to maintain and keep operational all year round. So what is an automated weather station? It's a suite of research-grade meteorology sensors for recording, storing, and transmitting measurements that generally require limited human interaction. I say generally, in our environment, there's more human interaction than sometimes we would like. Typical measurements from these weather stations include temperature and relative humidity, wind speed and wind direction. Some stations have ground temperature sensors, some have solar radiation sensors, and usually barometric pressure. Other equipment that is part of the station that's not taking measurements are the data loggers, the batteries, some of the enclosures to store and protect the equipment from the elements, solar panels for powering them, communications equipment, and a few of our stations, as you're aware, have webcams on them. Some things that we don't generally have on our particular network are precipitation measurement. It's really difficult when it's below freezing all the time, especially measuring snow on the East Coast. Visibility, we do have a visibility station that's currently not operational. And we hope to continue adding solar radiation and soil moisture and air quality measurements across the entirety of our network in the future. So I'll go into a little more detail on some of the basic station components. Station design can fluctuate from location to location depending on where it's located. Some of our sites have AC line power available. Most need solar and batteries. A few stations have nearby internet access, whereas most are very remote. Some of our stations have wind and some don't. Some are situated in areas where wind just can't be reliably measured. And due to the extremes of ice in the wintertime, anemometers generally won't survive on some of them. So starting with wind speed sensors, we are primarily focused in wind. I mean, that's what we're known for, or I'm focused on wind. I love the wind speed measurements and anemometers. And we use a variety of different wind measurement instruments across the organization. Most of our sites use what you'll see in the top left there, which is an RM Young 05108. The model is an Alpine HD. And I'll apologize now, I'm going to say a lot of model numbers, just how they go through my head. That is our primary workhorse. They are a fantastic unit that are very durable. They use extremely low power and they hold up well to icing conditions. They don't, however, hold up to summit observers hitting them with crowbars. That's something that they're not too fond of, and it happens somewhat regularly, if you can believe that. Sorry, observers. Another instrument that we use currently at Cannon Mountain is from Taylor Scientific, and it's a 6-cup anemometer, which has a heating element inside of it. And it goes with a heated vane. And in the lower center picture, you'll see at the top of that ice-covered tower, there is an anemometer there. That shows us what it looks like when the heater has failed. And below that, you'll see the directional vane, which the heater is working on. So we're going to be phasing that system out. The vane has since moved on. It's very hard to get parts for these older units now. And with the 6 cups, they're actually very prone to erroneous readings of overspeed. They can report a measurement up to about 40% higher than what the actual wind speed is due to upslope wind conditions. And lastly, on the right, you'll see what we're going to be putting at Cannon, which is an FT Technologies FT7. It's an acoustic resonance anemometer, which is pretty much a fancy way of saying an ultrasonic anemometer. And they measure wind speed and direction, and they have built-in heaters. They still use quite a bit of power, so these aren't something we use on our remote stations. However, in a place like Cannon, it should function well. And the only limitation with it is it has a maximum speed of about 150 miles an hour that it can record. There is a document showing a wind speed of around 200 on Cannon. We're not certain on the accuracy of that. It was measured with a cup style anemometer as well. However, this FT7, if we start seeing excess speeds on this, we'll of course upgrade it. Next are temperature and relative humidity probes. So each station has 2 probes on it, at least 2. And we use Campbell Scientific equipment again. We use what's called the CS215, which does temperature and relative humidity, and it has a type of serial connection to it. So the data logger communicates with the instrument returns the information. We also use what's called a T107, which is a resistance-based temperature probe. And that one only has temperature. And we use 2 sensors so that we can tell when one of them's not working correctly. And when you review data coming from the stations, you'll see that there's usually a very good fit between the 2. They're usually maybe 1/10 of a degree off each. Also in the picture, you'll see the housings for them, which are radiation shields. These are used to block direct sunlight from hitting the sensor, as well as giving it some shielding from the elements with relative humidity, for example. They take, they require frequent replacement. They break a lot in the ice. And again, there's something else that does not like being hit by crowbars. They're pretty fragile. And in the future, we're hoping you'll see a picture on the right. That's called an aspirated radiation shield, and that has a small fan inside. So it draws in and circulates the ambient air around the sensor. These are supposed to be more accurate, and we're hoping to deploy these across the auto road vertical profile, which we'll talk about in a bit. And just as a note, our nickname for these radiation shields are pineapples. Talked to a friend the other day who was using the term pineapples, and the other meteorologist looked at him like he had 3 heads. So I just want to say that, yes, we do use the term pineapples when we're referring to them. The heart of all of our weather stations are data loggers. We use several different flavors of them, all from Campbell Scientific, all from different generations. And think of these as small computers that can do quite a bit. They're very robust and work to extremely low temperatures. I believe the rating on some of them are -55°C, if I remember correctly. So they have multiple inputs depending on the model, and they can read inputs like 0 to 5 volt measurements, current measurements like 4 to 20 milliamp measurements. A lot of these are types of outputs that certain types of sensors give out. It can also do serial-based communication with devices, RS-485 communications, as well as some of them have built-in Wi-Fi. They have USB ports, so they're quite versatile. They have micro SD slots, so you can store data. And across our network, we have 3 primary flavors: the CR10, which is extremely old, which we're slowly upgrading. The CR1000 series are a little bit newer and have network capability. And then the newest that we're currently running are the Campbell Scientific CR6 models. And those are quite nice. They're fully featured, have great built-in interfaces. And for all of these, there's a programming language used to write the programs to acquire the data. Some other things that these do, if you look in the top right picture, you're going to see a vertical box with an orange connector on it. That's a relay control. These devices can turn off and on other devices. And we use that for things like turning webcams off at night. When the webcam can't see in the dark, there's no reason to power it off the battery systems. Other things that it'll do is the system will monitor its own internal voltage. And if the voltage drops below a certain threshold, say 11.2 volts or so, it'll shut down the communications array, depending on what type it is, turn it off and wait and run in a low power mode while still recording meteorological data until there's enough power in the batteries to enable the communications again. And we do this so that we can prioritize data over communications. So sometimes there'll be a delay in acquiring data. So what powers all of this, especially at a remote site, are very large batteries. our site on Wildcat, which you can see pictured on the left, has 8 240 amp hour batteries. Each one of these batteries is 160 pounds. They are no fun to move around. They're sealed AGM batteries or lead acid gel batteries. They're monsters, and they have a great amount of power that's stored in them. And the other thing about them is that they also work well at low temperatures. They can be charged at low temperatures, I should say. Their power output declines a little bit, but they can still be charged. The battery boxes are lined with an insulating foam, and that foam isn't to keep the batteries warm. It's more to protect them against rapid temperature shifts and shock of the battery. And to be honest with you, I'm not quite sure if that actually does anything or not. One thing I can tell you is that the ants in the area really love the foam and eat it and build gigantic nests inside some of the battery enclosures. The batteries, on the other hand, do not like the ants. And generally, once we get an ant infestation, things short, fuses blow, and stations go down. We hope to eventually be trying some of the new lithium iron phosphate batteries that can charge in somewhat low temperatures. They store a lot more power, and they're certainly a lot lighter and easier to carry out to our remote locations. Like here at Wildcat, at least we can take the lift up to the top, but still, even carrying these things from the lift to the ski patrol hut was a little bit of a challenge. Another part of the battery system is inside each of these enclosures where the data logger is, there are smaller battery backups, and you can see that pictured here. These are just smaller batteries that when either, if it's an AC powered station like this one here, which I believe is our Bretton Woods station, if the power goes out at its location, it'll run that data logger for about 24 to 48 hours because there's such low power usage. In that case, the network switch here will shut off and the radio will shut off to conserve power. Now, the communications part is something that I really enjoy. Again, being an IT person with a network background, I really love playing with these long-range microwave radios, and we're slowly upgrading older radios across our network. With the terrain and the distances and the extreme weather, as well as trees and mountains around here being made out of solid granite, communications can be quite a challenge. There really is no cellular communications in most of our areas where we have weather stations. So we'll use a lot of point-to-point and point-to-multipoint configurations for transmitting and receiving information. It can be difficult to get a live video stream from 8 miles away, but using some of the radios that we use, like Ubiquities, will certainly do it. And we'll go to next. Now, hopefully you guys aren't having all your eyeballs glaze over yet. So this is a communications map that shows the basic layout of our Mesonet. So what you'll see at the top here is our administrative office in Conway and our Summit Weather Station are two primary locations where we ingest data from our Mesonet. Each one of the subcolors that you'll see here is what we call a leg of the Mesonet. So they're each linked together in some pattern, usually of groups of radios or radios pointing at an access point. And for example, we'll have a link which is near Conway, which we call the Tyrol link. And that goes from a radio in our administrative office to the top of Cranmore Mountain, to the top of Tyrol Mountain, to a cell phone tower on Attitash, and then out to Mizpah Hut. Right now, that link is disabled for other reasons, but that's just an example of the type of communications that these radios use. A few lucky sites like Cannon and Highland Center have internet access. Bretton Woods has an access point on it. Our primary hub that most of you are probably familiar with is on Wildcat, which is one of the feed stations for one of our weather cameras. And that's actually an access point for about half of the Autoroad vertical profile stations. And again, I'll get to the Autoroad vertical profile because I keep mentioning that. A handy tool, seems I'm still on the radio path here, is called Ubiquity UISP Design Center. I believe it used to be called Link Mapper, or Ubiquity Link Mapper. And this allows you to do some testing before you deploy radios or figure out where you're going to put stations to determine line of sight communications. We're extremely lucky that we have the tallest site in 1,000 miles. It's usually a pretty good chance that further away from the mountain you are, the better chance you have line of sight. This tool allows you to place a radio and a receiver somewhere, and it will map the illumination field of that radio, and it will also estimate speeds that you'll get. And for example, our Wildcat radio from the summit to Wildcat is about 20 megabit, but from Wildcat to the summit's about 100 megabit, and that's just a factor of the types of radios we're using in that situation. Again, cell phones don't work. We hope to try some cell phone communication systems that are available from Campbell Scientific on some future Mesonet sites that we haven't built yet. And another thing we'd like to do is deploy some Starlinks as hubs in more relatively flat terrain, if such a thing exists in the area. And wrong direction. I'll let this repeat here. It's a video of former observer Adam Gill and one of our interns slowly digging out one of our Mesonet stations. And so with our data loggers, this is kind of hard to explain. These data loggers take multiple measurements every minute. So across the Mesonet, each data logger will sample each instrument on that particular station once every 10 seconds. And at a 1 minute interval, it will record the minimum, like let's take temperature, for example, the minimum temperature and record the timestamp for that. It'll take the maximum temperature and record the timestamp for that. And then it will give us the minute average. These stations will do the same thing at 1 minute intervals, 5 minute intervals, 15 minute intervals, 1 hour intervals, and 24-hour intervals. All of I gotta figure out how I wrote this here because I should just talk about it instead of trying to read what I have. So a 5 minute measurement will actually be an average of all the 10-second measurements taking over that 5 minute time span. And this is in a contrast to measurements taken at the summit. For example, our summit data loggers will actually take 5 measurements per second. So a 5 hertz rate of measurements. And we collect that data every 8 to 9 seconds to create 1 second resolution information. On the Mesonet, we collect about every 15 minutes. Once we've collected this data into our servers, they pass through a range of different sanity checks and some basic quality assurance. Does the temperature read 300 degrees or does it read 30? Obviously, it'll flag it if it reads 300, and we have seen that. And sometimes those 300 show up on the Mesonet map. It's stored by station name, date, and then it's synchronized out to Google Cloud, where the rest of you all can see it. If anybody wants to know more about that, because it's kind of confusing, please feel free to ask them the questions or send me an email. This is just a table showing some of the basic measurements and how they're stored. The left-hand column, you'll see the actual measurement name. The long name is just basically what the measurement is. Units, again, volts, degrees centigrade, degrees Fahrenheit, miles per hour, direction in degrees. And again, the sampling rate, it is checked every 10 seconds. So these stations take a measurement of what the wind speed is every 10 seconds. And when they're displayed, it will show you a 1 minute average with maybe a 1 minute maximum in there somewhere. So now the auto road vertical profile, which I've mentioned a few times. this is basically, and I thought it was fun to make a slide that I had to hit a button to make these sections come in. The auto road vertical profile is part of our current summit conditions page. It has nearly 20,000 daily viewers. It's extremely important for recreational safety in the White Mountains, especially in the Mount Washington area. It's a determining factor for opening non-hiking routes to the summit, like the COG and the Outer Road. It's basically a permanent weather balloon, and the National Weather Service assimilates the data hourly. And Jay is going to go into this. Jay, our Director of Weather Operations, is going to go into this in great detail. And it's necessary for nearly all mountain operations, transportation, shift changes, and it's spread out across the 8 miles of the Mount Washington Auto Road, spaced out about every 1,000 feet. And the outlier at 4,000 is because we needed a relay station in there so that it could transmit to Wildcat. This is just a top-down look of the Auto Road vertical profile, starting at the base of the Auto Road here, which is about 1,600 feet. The naming conventions are AR 2300 is 2,300 feet, 3,300 is 3,300 feet, and so on, going all the way up to the summit, with the summit station being the top of it. These are the easiest stations for us to access and maintain. So maintenance. This is a video of former Mesonet technician Pete Gagne doing some work on 5,300. It's one of our favorite sites because the view is just spectacular, and we try to pick nice weather to work on it. The maintenance and upkeep of the Mesonet stations is necessary and constant. The conditions are quite extreme all year round and really puts tremendous strain on the units. Everything breaks. Things you don't think will break, find a way to break. And again, it's just constant. Even while preparing for this, I was looking at some of the station data and found we have an anemometer that is not reporting, which will be on the short list for this week. In the spring, we visit each of the sites to check on their conditions to make sure that they survive the winter, check for graffiti. Generally, they're undamaged. People do like to stick stickers on the control boxes for some reason. When we find something that's wrong, we make plans to either hike in or drive to our stations that we can get to. Sometimes we get to take ski lifts or the tram at Cannon, which is extremely exciting and high winds. And we have to be very prepared when we go there. It's not something that you want to not have that one screwdriver, or if somebody decided to put the square-headed screws into the grounding bus bar and you don't have one of those, you don't want to have to turn around and go back out to reschedule for a different day. Again, we take the car, we take our vehicles up the auto road. For the station on the COG, which is the halfway house at 4,500, we get to take the train, which is great. And you can't tell in this picture, but it's pretty steep right there. And they stop the train for us. We get out with our gear, and then the train keeps going. And on the way back down, they pick us up, but the train doesn't stop. It goes really slow, but it doesn't stop. And we hop on. Again, we will hike to other stations, take ski lifts to a few. Just some other technical notes. Good electrical tape is really handy. That 3M88 is good in cold weather. Holds up to sunlight pretty well. And again, it's really good in cold weather. You can actually use it without it being super brittle. And good zip ties. Zip ties will break pretty quickly. And I'm also a believer that anything you zip tie is going to break, because then you have to undo the zip ties. What you'll see here in the picture is a video of our 4,500 station that I took, I believe, last year on a beautiful day. And then the picture on the right is what it looked like this spring. It decided to self-disassemble at some point. And so now this station needs a complete rebuild. Nothing really survived. The batteries are getting a bit tired there anyway. And this station has 6 batteries. Luckily, we'll be able to take the train up to this one. couple other different types of stations. The image on the left is our station on top of Tyrol Mountain. Several have these small Roan 25 towers. We don't have weather equipment on this particular tower. It's in the shade around the backside. Towers are fun to climb. The roofs aren't too bad. I have to say, I really dislike ladders. We have one station where ladders are necessary. I've stood on the skid of a helicopter hanging out the side of it with a video camera. It didn't bother me, but you put me about 6 feet up a ladder and it's no fun. Add attaches on a cell tower. So again, when we go to these sites, we have to be prepared, and we also work in pairs because it's easier to have somebody with you to help. This is an example of one of our internal displays that shows us what's going on with the station. We can see site voltages. We can see the internal temperatures of the data logger. We can see the voltage that the data logger is running at if it's running at a, say, 12 volts and the site's a 24-volt station. This particular one, you can see that wind direction is flatlined. Pretty obvious there we have a problem, and that ended up being an anemometer replacement. So what's next for the Mount Washington Regional Mesonet? I'm only going to briefly touch on this because Jay's going to talk about it, but we're looking to expand. We're working on potentially doubling our station count from 18 to about 35, 36. We've picked quite a few locations in Coos County that look excellent from a both recreational and safety perspective, as well as meteorologically important. A couple that I'm looking forward to are the ones at the 45th parallel and Hell's Gate. Those are just awesome spots if anybody's familiar with those. And another thing that's up and coming is an online data portal for real-time access for everybody to this Mesonet information. The portal's in its testing phases. This is an example from over the last 2 weeks of a plot that you can do right in the portal. You can see in the lower plot how much the purple line is relative humidity, and you can see how much it has actually been raining at the AR-16, which is the outer road base. So again, online data portal is coming soon. Hopefully more Mesonet stations are coming soon, and I believe that is all I have for this. Thank you guys for listening to me ramble for about, well, it looks like 32 minutes about IT stuff. Again, if anybody wants some really detailed, long descriptions of how any of this works, feel free to put something in the comments, or probably best give me a phone call so I can go on at length about this. And now I would like to introduce Jay. Jay Broccolo is our Director of Weather Operations.
Hi, everyone. Keith gave me a nice introduction, so I'm not going to tell you who I am, but I will share my screen with you. All right, so everyone can see that here. There's just my contact information and a nice view of the weather tower during some cold months. Let's get into it. So what does the observatory use the Mesonet for, right? So Mesonets serve a lot of different purposes depending on who's using it. They originally go back to kind of agriculture, where farmers were really using, they were curious about soil moisture when they needed to water their crops. Education, state departments use it a lot for emergency management. The energy industry is probably one of the biggest users of Mesonets. They often have them all over their power grids. Environmental research, and not just weather, plants, flowers, biology, all use Mesonet systems because meteorology has all those effects. Management of prescribed burns and unprescribed burns, wildfires, are really helpful in getting data from places where people are not really easily accessible to. And of course, transportation, logistics, and for what we use it the most for is weather forecasting, which leads us into what we use it for. So the observatory uses it mostly for forecasting, our own in-house and partner research, and for operational purposes. So the observatory's operations and also our partner operations, which we'll get into in a little bit here. But for forecasting, so here on the right, you see a picture of the New York State Mesonet system and one of their outputs. This is something that we will be working to. But given New York State's high density of Mesonet stations or automatic weather stations, that they can produce maps like this where you can see maximum gusts in localized areas, which you don't get in models really. So our Mesonet system really helps us localize our weather forecasts. We get higher resolution information that can help us improve our short and medium term weather forecasting down to a local scale. So our weather models that we use, for example, the global forecast system, the GFS that a lot of people are familiar with, that has a resolution of 18 kilometers. So in a square plot every 18 kilometers, essentially, you have one data point. And if you were to take that resolution and put it over the White Mountains, it would take 2 of those resolution points to make up the White Mountains. And our regional Mesonet has 18 in that same area. So using those, it really helps us build and inform our weather alerts. We can track frontal passages as they track from the Western Whites to the Eastern Whites, if you can consider that much of a distance, or north to south. Squall lines, much like the one we had Thursday night. Inversions, so I'll show you a nice graph of an inversion that Keith made. Boundary layer height and a vertical profile. So as you saw the autoroad vertical profile, it allows us to stack the atmosphere and see what's going on in the lower atmosphere. Microclimates, Keith talked about how they're called mesonets because a mesoscale is a scale. So we have micro scale, which would be very localized. Your town, Mount Washington, the Great Gulf would be considered a microclimate. And then you have your mesoscale climates, which could be New England or the state of New Hampshire. And mesoscale is really where you see your thunderstorms, mesoscale thunderstorms, so bigger thunderstorms in some of our nor'easters. And then we start getting into synoptic scale, which is large, half the country scale, big storms, again, nor'easters. And our Mesonet system also allows us to look at convective properties. So when we do have thunderstorms, we can see what the temperature is in lower elevations compared to higher elevations because we are in the mountains. So unlike states like Delaware or parts of New York, our Mesonet system is very much elevation dependent, which helps us, again, make a profile of the lower atmosphere to see how air masses at the lower levels are moving up to, say, summit level or above. Mountain waves as well, just like waves in the ocean, there are waves in the atmosphere. That's how lenticular waves form. That's how you see your Kelvin-Helmholtz waves or your KH waves, the ones that, well, look like ocean waves in the sky. And then lastly, lapse rates. There's some others for sure, but lapse rates are one that we're focusing on right now. And what a lapse rate is the change in temperature from, say, the base of a mountain to the summit. And what is that rate? What is the change in temperature, say, per 1,000 feet? So this is really where Mesonet systems come into use for us forecasting. As an example, during a frontal passage. So this is taken from one of our stations. And in the bottom left, you can see a model output. This is temperature advection. So it's essentially telling you how fast, the blue is telling you how fast the air is cooling. You can kind of see it here. It's temperature in Kelvin hour in frontogenesis, which is a change in temperature over 100 kilometers in over a 3-hour time period, which is shaded in the purple. And you can see it's very strong here, very dense. And this was taken at the same time back in February 2022 as this temperature instrument graph. So you can see the onset of when this frontal passage really started at 6:30 in the morning EST, which is pretty early. And you can see that the temperature dropped, 40 degrees in less than a 24-hour period, which is pretty wild. As you can see, it's a strong frontal passage, but this helps us, we'll see it first on the west side, and then we'll see it move through the mountains. And it really helps us nowcast and inform people out in the whites, hey, it's coming quick. You got to get down or get inside, or, be prepared. But it gives us a visual that helps us forecast these things. A lot of the times when you're outside, you feel it coming, but it's a little different when you can see it visually. Inversions, we talked about inversions. Now, this graph might not look too much at first, but we can just say that those brighter colors, those reds, are warmer temperatures. As you can see here, we're looking at 20 degrees Fahrenheit here. And then to the right of the screen where my mouse is, these darker temperatures are colder. Now, cold air is denser than warm air. So we would think that cold air would be at the surface. But in this case, it's not. So this is a 24-hour, could be, looks like it's about a 24-hour period. And you can see all the daytime heating. And then as we get into the nighttime, 10, 11 o'clock, 12 o'clock, you can see those warm temperatures are actually below our cooler temperatures. And then once the morning comes, you can kind of see that shift where these cold temperatures. So this is normal. This is not normal. But having our Mesonet system allows us not only to graph this, but tell our folks that are coming to the White Mountains, as well as ourselves, what to expect. Inversions are really interesting because they tend to trap pollution. So it's helpful to see when we do have an inversion so that we can relay, hey, the air quality may not be that good. This is why our visibility is less than what you may expect. Another reason why we have these Mesonet stations for, and this is really just a picture to kind of go along with what Keith was talking about, was our snow measurement. So we don't really have snow or precip at many of our Mesonet stations. And this isn't particularly one of our Mesonet stations, but that is one thing we would like to add in the future and that we're working on. We have this with icing. So it's very without constant attention. So we can do it at the summit because we have people up here going out to collect it and tending to it as needed. We can't necessarily do that at all of our Mesonet stations. But it is something we're working towards. Another thing that we use our Mesonet system for is research. And one of the big things we can use it for is studying climate trends. So what is the trend of temperature, say, over a 30-year period, right? Because a 30-year period is what we call a climatology. So here we have a lapse rate project that we're working on here, and Carl Philippoff, one of our next few nice graphs. But you can see the average temperature near surface lapse rate distribution and how that changes from season to season. So you can see in the summer, we have really tight lapse rates. And then in the winter, they get really spread out. And then in the shoulder season, spring and fall, they're also kind of chaotic. But this helps us forecast because knowing how the temperature changes from the base of the mountain to the summit allows us to say, well, how is the precipitation going to change? Is the precipitation starting off as a water vapor at the bottom of the summit? And will it precipitate out as snow? Will it precipitate out as water? It's not just about what the temperature is, but the evolution of that, right? So sleet, for example, it may form, our precipitation may fall as snow at the summit. But by the time it gets to the valley, it may go through a melting period and fall in the valley as sleet. So having this type of data can help us forecast that. we can tell you that, yes, you will be experiencing sleet in the valley, but not up on the summit. And for those people coming up into the whites, that's really valuable information. But not just lapse rates. So other types of weather phenomena, I mean, even thunderstorms or frontal passages, we can test a 30-year period of soil moisture, right? What is the available moisture content for plants? And water management. Water management is the main use for most mesonets out west, Snowtel or Meso West. That's their main purpose, is to judge water management. So all the snow that falls in the winter is then used as water resources in the summer, and they need to manage that. And the best way to do that is to understand how much snow depth they have in the western area. So some more charts to look at here. Looking at lapse rates is just some more ARVP temperature data. You can see some statistical box and whisker plots there on the bottom left. And again, in the summer, that bottom left one, you can see there's not much variability. And then in the winter, it's a little bit more. In our spring and fall, where we seem to have the most change, right? We see those really warm days and those cold temperatures at nights. Well, look at that. It's presenting itself in the data, which is nice to see. When it doesn't present itself in the data, that tells us, well, maybe we didn't really know what we were talking about. But this is really helpful. It solidifies what we're trying to investigate. And then the seasonal lapse rates, again, the Tmax, T average, and Tmin. You can again see in the winter we're pretty stable there, spring, summer, and fall. But we haven't taken out inversions in here. So as you saw before, the inversions can really actually throw this data off. So that's something to come in the future. So some of the other things that we use the Mesonet for that Keith touched on was our operations, our transportation logistics. It's fun to look at the snowcat, but there's a lot of things that go on in the observatory, and our transportation logistics is arguably one of the most important ones, because without it, we can't staff the weather station. And safety is a massive concern for my operations, our transportation coordinators, operations, all the observers, everyone up here. And it's not just the observatory, it's State Park in the winter. It's the auto road in the winter and in the summer, and the COG. But for the observatory purposes, yeah, we use the Mesonet, specifically the auto road, to judge our maintenance schedule and the snowcat and our transportation. When we go up in truck and van and it's the shoulder season, do we need chains? What's the temperature like at 5,300? The bottom of the base looks good, but are we going to be having boilerplate ice up at 5,300 because we had a frontal passage come through at night to freeze everything very quickly that melted, say, from the passage of a warm front. And this is, mind you, we have everything with us, but if we can use our system to do less work, that's always great. But even for our partner operations, our partners on the mountain and elsewhere, the auto road needs to know the road conditions, as well as weather conditions for their people driving up the road. We have a camera that looks at 5 Mile, which is one of the harder places to plow, and that can be really helpful because we can see what we're getting into, assuming we're not in the fog, which isn't very often. The COG Railroad as well. They need to know their weather conditions, which is something we're getting into, building out some weather stations along the COG. But for education purposes as well, people take these van rides up to the auto road and they spend 45 minutes in the COG, and on the way up they have their attendees talking about Mount Washington weather, and they can do that because of our Mesonet. The Appalachian Mountain Club is a massive user. They don't actively use it as we do, but it helps in hiker awareness. It informs our higher summits forecast, and it also houses a lot of the communications that we use around the summit and our partners. Keith touched to the communication section, but a lot of it is how, say, for example, the Mount Washington Avalanche Center can transmit their data is actually over our Mesonet. So there's snow reports that they use from us to judge their avalanche warnings. It's an integral part, and this is why we consider our Mount Washington regional Mesonet as more of an infrastructure rather than tools, because it is an infrastructure. We use it for our operations. And then just to lastly touch on a couple of my favorite things and things that we're really excited about, the future of Mount Washington Regional Mesonet. One of the things we're trying to add to this is called an atmospheric LiDAR, which you can see that picture to the top left, but to the top right there, over here, this little thing right here is the LiDAR, but it actually shoots up into the atmosphere and it can profile the lower atmosphere. So these would be like our mountain waves, right? And we can measure those and the winds before it actually comes to the summit. So it's great that we can forecast the winds using model outputs and our own intuition and know-how and skill set. But it's great if we could actually profile the winds before they come to the summit. And we can do that with an atmospheric LiDAR. But not just wind, we can do it with a lot of other things, pollution, temperature. So that will really expand our research capabilities. And another thing that our Mesonet does in collaboration, say with an atmospheric LiDAR, is kind of more into the research, but this is some of the stuff that we can do. So this graph here is actually measuring backscatter. So attenuated backscatter, which is how the LiDAR works, but what it's physically measuring is the boundary layer. So within the boundary layer, that's where most all of our weather happens. And the observatory sits at around 800 millibars or hectopascals. So our atmospheric LiDAR could potentially profile the atmosphere above our summit and let us know where the boundary layer is. This would be really helpful in judging cloud deck. You know, when is the summit going to be in the fog? When are we not going to be in the fog? Are we going to have an undercast? One of my biggest forecast busts, I was just being off by 500 feet. I said we'd be in the clouds all day. And it ended up being one of the most sunny days I've ever experienced on the summit. However, for that entire day, there was undercast anywhere from 300 to 500 feet below us, which extended for 2,000 feet down. So while a massive bust, technically, I was really only off by a few hundred feet, but something like this would have been really helpful and can make us much more accurate and precise with our forecasts. And then finally, just a bigger view of what we plan on doing with our Mesonet system. So these are all the stations that we plan on adding if we're successful in our funding. But what I really want to point out, and I know Keith is really excited about these ones up here and so forth, and I am too. But I have to be honest, I am most excited about these ones down here, which are pretty high resolution. They're going up and up the Cog Railway, and also some of these surrounding to the northwest. Now, our predominant wind speed is from the west and northwest. So again, having these Mesonet stations as a precursor to our weather hitting the mountain will be very helpful, not only for the observer and our forecasting and our research, but to all of you who love recreating in the White Mountains. And from there, I will end it. You've seen this same Mesonet station multiple times throughout the presentation. And if you notice, these solar panels are all at different heights. So while Keith was talking about maintenance, some of the most maintenance we have to do is just digging out the Mesonet stations. And that's all I have. You can see my contact information there. And Brian, I'll pass it back to you.
Hey, thanks so much, Jay. Thanks, Keith. I really appreciate both of you guys presenting this evening. I know we got some questions that are sitting already in the Q&A queue right there. Keith, I know you've been answering a couple there, and I'd like to encourage everybody who's joining us on Zoom to submit a question, whatever comes to mind around any of the information Keith or Jay shared around the Mesonet, its use here at Mount Washington, and even questions just even related to that. So happy to get into that, get to as many questions as we can, and I'll pass them back and forth a little bit here. This might be a good, well, actually, I don't know who to throw this one to. Maybe Keith, you to start, but William was curious about, so except for possibly wind, why such a high sampling rate recorded in the Mesonet system? Because you mentioned, I mean, in some cases it's, a sampling rate of, every several seconds, even for some variables like temperature. Is that just like a standard that's across the meteorological sort of fields, or is there like an operational or research need, or what?
Well, there's two simple answers, I guess, for that. One has to do with the data logger and the programming and the scan function of the data logger. So it has two primary scan functions. It has a regular scan rate, and it also has a slow scan rate. And so you can have the data logger do things at different intervals, but you can really only do 2 intervals. So for example, with we had an instrument on the summit that we wanted to sample every 20 minutes. That goes in the slow scan. The thing with the Mesonet being at 10 seconds is that it allows us to run a standard deviation on the incoming data and look for things that don't fit. And we can catch it sooner versus if we were running, just a 1 minute scan, we'd be taking a sample, and a 1 minute sample, you can throw this back and forth, but a 1 minute sample may not be as accurate, especially with the rapid shifts we see in temperature and precipitation. And again, with the functionality of the data logger, if you want to sample wind at a higher speed, generally you're going to throw the sampling in for the other instrumentation into the same function that samples the wind. It's just, again, it's just how the data logger is programmed for us.
Yeah, and as you mentioned, Keith, I mean, certainly I guess that resolution, depending on what it is, like Jay was showing before, and even some of your figures as well. Quick frontal passage, some sort of phenomena, spike in temperature or wind speed, perhaps, and maybe you miss it if you don't have that data there. And more is more, I guess, in this case. And it's so long as your systems can hold up and can capture all that data, I guess why not is sort of the other piece. I'm really curious. This is a great question, suggestion from Karen. Jay, Karen's suggesting, hey, would it be possible in a future presentation how Mesonet data could be used to forecast very local phenomena for hikers, such as she suggests ground frost, from the dew point, or undercast. I know we get that question a lot from folks who are like, hey, I really want to get to the top of the mountains. When's the undercast going to happen? Or, other conditions like that. In that question, I mean, I guess, Jay, I wonder if there are like maybe some specific scenarios that you could recall from forecasts you've had to do where you're looking at, the Mesonet data and what that means for hikers as well in your forecast.
Yeah, I mean, today was actually a great example. We had an unhealthy air quality because of all the smoke around. So we were looking to see if we could see an inversion, because if we had an inversion, it would have trapped a lot of that pollution and actually would have made the air quality worse in the lower levels. But because we didn't have an inversion, you can actually see the haze and the smoke higher, so it disperses it quite a bit. But yes, the Mesonet system or any of the automatic weather stations absolutely helps us forecast locally more so, because we can't see that in the models. The resolution is too low. Satellite data is pretty good, but a lot of satellite data is thrown out. So we can look at the picture, but again, the satellite is quite far away, and at that small scale, really hard. But just looking at dew point and temperature can tell us a lot about the air mass. It's very helpful, and the more that we have, the more the better we are at forecasting it.
Yeah, absolutely. And I'm sure there are other examples that, give it a second, you can probably think of all the times you've used it, and colleagues as well.
Yeah, I mean, even in reports where people reach out to us and are like, hey, you know, when did this phenomena happen? And you know, we can tell you when it happens at the summit, but that kind of goes also into the sampling rate, because we need to have, you know, like he said, it may be 15 minutes that it's being recorded, but it's sampling at all that time. So we're not necessarily missing anything. So it's really helpful in just in timing and understanding, because a lot of times, right, like the sun goes down, it's like, oh, we have a thunderstorm approaching, but the sun's going down, which is a lot of the energy needed in thunderstorms. So, you know, if we can see that there's a really high dew point like there has been of 70 degrees, because a lot of people think humidity is how you judge moisture in the atmosphere, but it's dew point. Humidity actually comes from dew point. So it's really helpful for us.
I'm sure, yeah. And just thinking for a second here, Keith, I know John has a couple questions and related to, I guess, well, one for starters, John's asking maybe a question around communications. I'm not familiar, LORA, Laura, if that's something that you've looked into or is ever used for communications with the Mesonet system.
So I've looked into it. I actually assembled a small LoRa gateway for the Plymouth State snow monitoring project. That was in one of the slides that Jay showed, which was basically a temperature ladder. And in building out the acquisition system and the communication system for that, I looked into a couple different things, and LoRa being one of them. However, I ended up using an ESP32 based serial radio, for those that know what that is. And it was extremely low power, and we pulled a 7-mile link out of that thing that was great and reliable out of just this little tiny Arduino based or Raspberry Pi based radio. That was a fun project.
And so similarly, I mean, I know you, I mean, both Jay and Keith, you've both been spouting some, you know, some of the specifics of the inside, I guess, tips and tricks a little bit in terms of the special things that you all have to deal with in managing and using this system. I know, having been involved myself, Jay, Keith, you guys, related to John's question here, is asking if there's open documentation around the Mesonet infrastructure. You both were key authors for the a paper just published earlier this year. John, I'm happy to share that information with you. Unfortunately, it does require a subscription to that journal, but that information is at least out to the scientific community at the moment. It was a big effort, and certainly I think for all of us there are a lot of lessons learned, including Jay, I'll put you on the spot. Do you remember how old the oldest Mesonet station now is? I'm not sure if Keith had covered that.
Oh, well, I think it was what, 2003, 2004.
I think, yeah, maybe even
Yeah.
2002. I mean, these stations now almost going for a full climatology, and I was just wondering, Jay, if you might speak to like what value might that have? I mean, there aren't necessarily a ton of networks that are out there that have existed for a terribly long amount of time.
Yeah, I mean, you know, especially when it comes to climate, looking at 1 year is kind of pointless. It doesn't really do much for us. The more years that we have to look at, now we can actually start to put trends together. And the way that NOAA describes a climatology is a 30-year period. And I'm not even saying that 30 years is necessarily enough, but it's getting to the point where now you can take multiple 30-year periods and start comparing them to each other. So the fact that we have almost a full 30-year period, we can do an initial study on all those different climate trends that we brought up earlier, and can start moving forward so that the next 30 years we have that initial base to compare to.
Yeah, I mean, I know oftentimes we're talking in terms of weather and what's happening right now, but that brings into mind a whole nother realm. Well, Donna here asked a good question. It's been upvoted as well. Basically, let me apologies if I'm translating this or putting words in the mouth here, but basically Donna is asking if you had the dream or ideal Mesonet, how many stations would you have? Where would they be? What would you do? All the support and helpers in the world. I mean, what would this look like potentially?
Oh God, I mean, I think that looks different to each person. I'll just keep it to the state of New Hampshire because ultimately I think it would be awesome to have them across the planet. Um, but if I would like to have them all over the state of New Hampshire. But I think what's really important is that each state starts collaborating because our air doesn't originate in New Hampshire. It comes from New York, Vermont, the states to the west of us. So the higher resolution, the more Mesonet stations that we have with more instruments, that would be great. So, oh God, I would say number of stations, 36. I'm just gonna say like 75 stations in the state of New Hampshire would be fantastic. A couple LiDARs throughout the state. I think ultimately I would like to have them around all ski resorts, like so that we can establish lapse rates for all the mountains. I think it'd be really helpful for the ski community and understanding how snow precipitation is changing, if it is changing. People seem to think it is. It seems to be changing, but it would be great to put that data to it and visualize it.
Keith, you think you can handle 75 stations? Oh, sorry, this is an ideal scenario. That's right.
Ideally, I'd have some help.
Yeah.
Absolutely. Well, oh man, there are maybe we'll have time for just a couple more questions. I know we've been going long, but there are some fantastic questions that have come up here. Another one from Kenneth, who's wondering. So Kenneth says, we've been measuring wind direction and speed for a very long time, but seemingly continue to have great difficulty overcoming obstacles that interfere with those measurements. Is there some fundamental challenge that we just can get a handle on? So I'm not sure the exact scenario there, but I don't know if you could speak to either Jay or Keith, some of the difficulties around sighting and what are the things you have to either just give up on or deal with or accept, around interference and turbulence, from other things, maybe downwind of an instrument.
Yeah, sure. I think it's the icing. That's just the biggest issue. Most everything else we've been able to manage for the most part. But it's the icing, the propeller anemometers, the RM Youngs, they're fantastic. They're so accurate, very precise. But as soon as those propellers start accumulating ice, or the accuracy it plummets. And you can't heat plastic really. And and electricity, right? So we're in a mountain environment. The mountain itself is in the fog arguably 60% of the time, roughly. So how do you power the batteries? The solar panels are great, but I think as solar panels have come a long way in the last 20 years, batteries have come a long way in the last 20 years. So it's the technological advances that really help us. So I think there isn't really anything that we haven't made progress on, but icing is the one slowing us up the most for sure.
All right, well, I might just end with this last one because it's a good excuse perhaps for you both to talk a little bit about some conversations you've had elsewhere in the community. But Anonymous asks, hey, why not cooperate with the state of Vermont or UVM? What if what interactions are you having with other Mesonet systems out there currently, and where do you see, I guess, this regional Mesonet fitting in with the broader Mesonet community? And we'll leave with that one.
Yeah, so that is actually something that we've been involved in. Keith and I have been doing a lot of work. We actually attend these monthly meetings with several representatives, including Maine, New Hampshire, Vermont, New York as well. So far, it's just really those 4 states, but it is well, let me see if I can get this, NENMO, so Northeastern Network of Mountaintop Observatories. Yeah, that's it. So we are there's a grant in right now, led by one of the people at UVM, Joshua Bennis, to collaborate and kind of build like an API that Keith showed you, where it will show you initial data and then bring you to each Mesonet's respective site for data. So we are trying to, because, you know, like the person who asked that question, it's we do need to collaborate, and the more communication between states, the better. And that includes out west, right? Because our weather, we're the tailpipe of America, as Keith said. So wherever, and Canada as well. I mean, look at the smoke that we're getting right now. The smoke is, most of it's not originating in the US. So yeah, there definitely needs to be collaboration, but I think the big problem with that is everyone puts so much work into their Mesonets. It takes a lot of time and organic relationship building to really get that going.
Well,
And it creates a ton of work for Keith.
That's right. That's right. Yeah. Well, the more the merrier, though. I've seen you guys interact with those other constituents, and I know there's a lot to be offered every time you get involved there, and it's also I know you've also gained a lot from those communities too. So, well, with that, thank you both so much for presenting tonight. I really appreciate it. Our staff is also coming off of a great Seek the Peak fundraiser weekend, and I put these two up to it. Jay is covering the night shift as well and getting ready for thunderstorms to hit the summit. So thanks to both of you so much. Thanks to everyone who joined the program this evening. If you enjoyed the program, would definitely encourage you to go over to mountwashington.org and hit the donate button in the upper right hand corner there. It's a free program. We'd like to keep it that way, but if you have been enjoying the series, certainly we'd love for you to support the program. If you have thoughts about tonight's program or even some suggestions like for future programs like Karen from before, please feel free to fill out the Google Form survey that'll follow in the Zoom window here and also in our follow-up email as well. And then finally, don't forget to join us for our upcoming Science in the Mountains programs. Our next one is Tuesday, August 15th. That'll feature Observatory staff where they'll provide our annual update on our current research projects. And on September 19th, we're looking forward to hosting Dr. Jim Steenberg from the University of Utah. He will be discussing the greatest snow on Earth with a closer look at what makes the Wasatch Range in Utah a world-class skier destination. So don't forget to register for those programs and watch any previous programs you might have missed over at mountwashington.org/SITM. And we'll see you all again soon. Have a great night. Take care, Jay. See you later, Keith. Bye, everybody. Take care.